All right, let's talk about the strong, weak acids and bases. So I already told you about the list of strong acids that I want you to memorize. HCl, HBr, HI, and then same thing but with 4 oxygens, and the same thing but with 3 oxygens, right? So that's the list of the 9 strong acids that derive from chloride, bromide, and iodide. Or really, I should say chlorine, bromine, and iodine. And also sulfuric acid and nitric acid. Anything else is going to be considered a weak acid. Now, what we ultimately mean when we say that the acids are strong is that when you add them to water, they will give off all of the H plus that they have. So let's say you have a 1 molar concentration of perchloric acid. The moment you add it to water, it will fully dissociate to give you 1 molar concentration of H3O plus. Full dissociation occurs with strong acids. And because of that, and the fact that they're forming now charged species, the charged species, which technically can be used to conduct electricity, are known as electrolytes. So these are strong electrolyte solutions because everything is dissolving fully into ions. All right, so to some degree, yes, the solubility rules also play a role because you may remember there was always the always soluble cations and anions. Those are the things that fully dissolve in water, and kind of like the acids that fully dissociate in water. This will also be considered strong electrolytes, right? They do dissolve fully in water, and you have them present in there. So the strong electrolytes are derived from strong acids or bases, and also soluble salts. And you may have heard about them and be most familiar in terms of your drinks, your sports drinks or anything else that tells you, oh, this is rich in electrolytes. That means that it has ions present in there, and you actually do need them because your nerve cells actually do use ions to transmit the the actual information to your brain, and from your brain to your muscles and organs. Basically, you have neuron cells right here that are exchanging information by shooting a stream of ions, which basically kind of create an electrical current. And so having electrolytes is absolutely of utmost importance because without them, the neurons cannot exchange information. And if that happens, you basically are dead. You will not be able to function. And right here, so this is a drawing of the event, but right here they're showing you the actual two cells coming together to undergo the synapses event, which is basically the firing of electrolytes from one neuron to another. All right, typical ones are potassium, sodium, chloride, calcium, magnesium. Potassium being the one that you want to have a little bit more in your diet. Sodium is associated with heart problems, so you don't want to have too much sodium intake. You do need it, right? So you should not avoid sodium. That would be a bad idea. But you want to limit the excess amount of sodium that you're taking in, because if you start messing with the ratio of potassium to sodium, that's when your heart problems start happening. All right, now the more relevant portion about it, yes, the ions or the salts that are soluble, fully dissolving water producing ions, the strong acids and bases, fully dissolving water to give you ions. But the reason they're called electrolytes is because they serve as a medium to conduct electricity. So what you can see here in this picture is that there's a light bulb connected to an outlet that's powering the light bulb. But notice that the cables are separated here. You have these alligator clips, the red one that's connecting to the solution here, and then the black one that's connected also to the solution. The two cables are not in contact with each other, but the solution right here that has the strong electrolyte is allowing electricity to flow through, producing the actual light that you see for your incandescent light bulb right here. So this is a requirement to conduct electricity. Uh, Having a stronger electrolytes leads to higher currents. And in essence, it is the presence of electrolytes in water that can electrocute you, right? So it's not so much that water ends up electrocuting you, it's the presence of the ions in the water that are doing the trick in terms of passing all that much current and, basically frying you up if by accident you happen to have anything electrical connected around that falls in water. So electro basically stands for conductivity of electricity, and light stands for separate or dissociate, hence the fact that adding a strong substance to water ends up yielding ions, separating them in essence. All right, so anything else that's a weak acid, right, which is not a list of the 11 ones that are considered strong, anything else will be considered a weak acid. And the idea with weak acids is that unlike the strong acids, they will only partly dissociate into ions. So you will form some hydronium and you will form some, in this case, chloride, but a good chunk of the HClO2 will remain as HClO2. So only a small amount of it will actually dissociate. And because of this partial dissociation, we refer to them as weak electrolytes. The same thing happens with salts that are insoluble. Some of it will dissolve, but it will be a very minute extent. And water can also be considered that because water is technically a weak acid or a weak base. It dissociates to a small extent, as you will find out in a little bit, but it is a very small extent. In fact, if you have water, or in this case, a sugar water solution, you can see that there is a little bit of flow here, meaning that there is a little bit of conduction happening, but it's very tiny and very minute compared to what we saw before with the strong electrolytes, because the dissociation is only partial. All right, and here you can see it. Yeah, this is now pure water. You have a few extra particles there to basically prevent the presence of any ions being present in water. So they're basically sucking up all the ions and keeping only the pure water around. And pure water also, you see barely any electricity flowing through here. All right, now let's talk about water a little bit more in detail. Now, as I just implied, water being a weak acid or a weak base, it will dissociate partially in solution. In fact, because water is amphoteric, it can actually react with itself. Like one molecule of water could behave as an acid, and then second molecule of water can behave as a base, in which case the base accepts an H plus, the acid donates an H plus, and in the process you form H3O plus and hydroxide. Now for pure water, this happens to an extent of 10 to the negative 7 molar concentration. That's the highest concentration of H3O plus and hydroxide you can get from only water dissociating into the ions. So this is ultimately what allows some electricity to uh, be conducted in water, but it's very small, right? This is technically in the realm of zero point 0.1 micromolar or 100 nanomolar, if you want to look at it that way. So it's a very small value. So there is a constant that we're going to talk about a little bit more in detail in the next lecture, but I'm going to introduce it right now. It's called the equilibrium constant. This one in particular is the equilibrium constant of water auto-dissociating into hydronium and hydroxide. And this constant is simply the multiplication of the hydronium concentration and the hydroxide concentration together, which for pure water is going to be 10 to the negative 7 times 10 to the negative 7, which undoubtedly ends up being 10 to the negative 14. So you don't even need to necessarily call this pKw. You could just say 10 to the negative 14 equals hydronium concentration times hydroxide concentration. But you could use logarithms to deal with the exponents. If you take the negative log of both sides, you get the negative log of Kw, and the negative log of hydronium times hydroxide using the rules of logs is the same thing as writing negative log of hydronium plus the negative log of hydroxide. So this is the splitting of logs. This is one of the rules of logarithms that hopefully you do remember. But the negative log is a function that we utilize. In fact, the function is called p. This is the p function. And quite simply, all that happens is that the negative log of something ends up being the p of something. So negative log of Kw is the pKw. The negative log of H plus is the pH. The negative log of hydroxide is the pOH. So the negative log is simply function p. And you could even think of it this way. This is the negative log of x. That's the f of x function, right? In this case, the x could be k, or it could be H plus, or it could be OH minus, in which case that would pH, pOH, pK. But more importantly, pH plus pOH have to equal 14 because the negative log of 10 to the negative 14 is 14. All right, so that's a relationship. pH plus pOH equals 14, and 10 to the negative 14 equals hydronium plus hydroxide. Those are good relationships to keep in mind. All right, so we're going to do some pH calculations right now involving the equations that we just looked at. And there's a number of ways that we can go about solving for this problem. All right, so we have the pure water situation, in which case the concentration of both hydroxide and hydronium is 10 to negative 7. If the concentration of hydronium is 10 to negative 7, the pH, which is the negative log of hydronium, will have to be the negative log of 10 to negative 7, or in other words, 7. So that's the pH of pure water, neutral water. All right, now let's see what happens if the hydronium concentration is a little bit higher, 2 times 10 to the negative 7. This will happen if you start adding an acidic substance to water. All right, so in this case, the hydroxide concentration, we're going to find it out using the equation here. We have Kw equals hydronium times hydroxide. Right now we have the hydronium concentration, so we could solve for the hydroxide concentration by dividing both sides with the hydronium concentration. So we have 10 to the negative 14 divided by 2 times 10 to the negative 7. And if you do this in your calculators, I highly recommend that you use parentheses. In fact, probably you want to use parentheses period, or else your answer is going to end up, totally wrong. So if you perform this calculation, you're going to end up with 5 times 10 to the negative 8, I believe. Yes, 5 times 10 to the negative 8 for the hydroxide concentration. Now the pH, once again, you take the negative log of hydronium, which is the negative log of 2 times 10 to the negative 7 in this example. And that gives you a value that is now a little less than 7, 6.69. All right, now there's another way to get the hydroxide concentration, and it's by first determining the pOH. We know that the pH plus pOH equals 14. So now that we know the pH is 6.69, we could subtract that from 14 to give us the pOH. So 14 minus 6.69 equals 7.31. And to get the hydroxide concentration for this, we do something known as the anti-log. We raise 10 to the negative pOH. The same way that to get the hydronium concentration for pH, we will have to raise 10 to the negative pH. So 10 to the negative pOH is the hydroxide concentration. The pOH is 7.31, so 10 to the negative 7.31. Your calculator will tell you that's actually equal to 5 times 10 to the negative 8. So either way, you can find out the hydroxide concentration. All right, now let's see what happens when we start with the hydroxide concentration instead. So now we have 3 times 10 to the negative 3. We can use this equation to find the hydronium concentration. Divide 10 to the negative 14 by the hydroxide concentration, which is 3 times 10 to the negative 13. Use parentheses if you're going to perform this type of calculation. This will give you 3.33 times 10 to the negative 2 for the hydronium concentration, which then you can use to get the pH. Negative log of hydronium, in this case 3.33 times 10 to the negative 2, tells you that the pH is 1.51. Alternatively, you could first get the pOH. Since you have the hydroxide concentration, take the negative log of hydroxide, that will give you the pOH, which in this case is 12.5. Subtract the pOH from 14 to get the pH. So 14 minus 12.5 will give you the 1.5. Before we had 1.52, so 1.5 is not that far off. And then take the anti-log, of the pH, so 10 to the negative pH to get to the hydronium concentration, which is going to be 3.2 times 10 to the negative 2, which is pretty close to what we had before. All right, so these are the different ways in which you go about solving for the hydronium concentration, the hydroxide concentration, the pH, and the pOH. Now let's take a look at another example. Let's say we start with the pH, 7.30, and we want to find the other values. All right, what we can do is take first the anti-log of the pH, and that will be 10 to the negative pH, or 10 to the negative 7.3 in this example. That will equal 5 times 10 to the negative 8 concentration for hydronium. At this point, we could use the pH to get the pOH, so subtract 7.3 from 14 to get a pOH. In this case, that is 6.7. And now take the anti-log of the pOH, so 10 to the negative pOH is hydroxide concentration, which means that 10 to the negative 6.7 will equal 2 times 10 to the negative 7 hydroxide. So this is one of the ways in which you can go about finding out the two concentrations. All right, now hydroxide, once again, if we go even to higher values, we get 3 times 10 to the negative second. And if you apply the same logic, use the Kw equation to find the hydronium concentration, take the negative log of hydronium to find the pH, you'll find out the following values. All right, what I want to highlight though, and this is pretty important, is that for the solutions where the acid concentration is higher than the base concentration, you're dealing with an acidic solution. And check this out, for the acidic solutions, the pH is always less than 7. But where the solutions end up having higher hydroxide concentration than you do have hydronium, these are considered as basic solutions. And for basic solutions, the pH is higher than 7. All right, so acidic solution, less than 7 pH. Basic solution, greater than 7 pH. So this is to say that if you do add an acidic solution to water, the pH better end up being lower than 7. It doesn't need to be very much lower than 7. It could be 6.99. That still counts as being lower than 7, but it has to be lower than 7. If you add a basic substance, the pH has to be greater than 7. It could even be 7.01, and that will still count as being higher than 7. And when you're mixing acids and bases, at that point you may need to look at which one is the limiting reactant to find out which one substance is the excess substance to determine whether you end up with a basic or acidic solution at the end. And just for reference, the pH scale that you're going to be basing this on goes from 0 to 14, right? So that's usually where you're going to be in terms of using water as your solvent. All right, and in terms of the experiments, which you could carry out if you were in the lab, you have various means of doing this. We have pH papers that if you submerge partly the paper in water, you can see the color change, and from the color change, you can determine what the pH is. And then there's other ones that just tell you whether the solution is acidic or not. The blue litmus paper, if you dip it in acidic water, it will turn red, telling you that the water is acidic. And the red litmus paper will, if you submerge it in basic water, it will turn blue, telling you that the solution is basic. In addition to that, we actually have pH meters that you can add to your solution and measure the pH directly after you calibrate them. So this means to doing all of that. All right, so in the next video, I will talk to you about buffers.